In today's lesson, we'll be looking at the topic of logic gates. So we will first begin with a general definition, and then we will get down to business of what we actually need to understand with regards to this particular topic. So just give me a minute. Let me switch the displays. There we go. So everybody can see my slides, right? Okay. So with regards to the subject of logic gates, which falls under what we call digital electronics, this is essentially where the hardware meets the software. As IT people, we are more concerned with software in general, but to some degree, we need to have a proper understanding of how computer hardware actually operates. So biologically speaking, if I'm studying the field or the subject of biology, I can say that the smallest unit of life is a cell. So I can go ahead and describe what makes up a cell and how a cell behaves and so on. In electronics, the digital circuit is probably the smallest unit that we can actually investigate in terms of the components that make up the primary components of hardware. So the term logic gate literally refers to a switch. A switch is the smallest component that we typically can measure and we can interact with regards to a digital piece of electronic or an electronic device to be specific. So the controlling of this switch is what gives the computer the ability to perform its operation. So if you remember from the first lesson, we said a computer is a device that can accept input, process it, and generate output. So that input, process, output sequence, that input, process, output sequence can be reduced and understood by looking at the internal components and the hardware of the computer and how they pretty much operate. So the term logic here, English definition, simply means a systematic way of thinking. And when you look at something logical, typically what you're trying to do is you're trying to understand whether the thing is true or whether it is false. So everything that happens inside a computer in terms of processing has to do with this true or false value. For now, this won't make too much sense. So let me begin, as usual, by giving you a more contextual example with regards to this subject matter. So if you take a look at my board here, let's let's do a small example. Let me explain to you how a computer actually works uh, at the digital level. So here I'm drawing a motor. A motor is essentially an electronic device that when you apply electricity to it, it has a spindle and it spins. So if I went, say, online to Google the image of an electronic motor, what you see under images is this device. So this device, basically, when you apply electricity to it, it creates a current that coils a certain spindle and this is how most devices work. You can have a mechanical motor, which is what motor cars use, and you can have an electric motor, which basically just instead of using chemical energy, it uses electricity to actually cause a spin. So by controlling the flow of electricity to this motor, I can make it spin or I can make it stop spinning. That makes sense, right? So in other words, if I have this motor, when the electric current applied to it is in the on state, it equals to a spin. When it's in the off state, it, of course, does not spin. That makes sense, right? Can I get thumbs up, people? So remember to use your reactions, right? It makes sense. Turn it on, it spins. Turn it off, it doesn't spin. So here we're going to use this motor to illustrate, to basically illustrate something interesting about how computer devices work. So this motor, imagine if I attach it to the skeleton of a toy car. So here on this toy car, I'm creating basically the skeleton. So here you have the axle and the tires or the wheels. So imagine if I were to mount this type of motor onto this axle and I connect it to the shaft here. So this, let's call this motor A. So when I turn on motor A, it begins to spin in a particular direction and it causes the wheels to spin forward. So if I attach this motor to this spindle and I turn it on, it will give the car, the toy car, a behavior, and the behavior will be to move forward in a straight line. That makes sense, right? Now, imagine if I take the same motor and I flip it upside down. In other words, it's facing one direction and I flip it upside down facing the other direction. Of spin will reverse. So that means if I take the same type of motor and I apply it, and this time I flip it, and let's say I call it motor B, attach it to the same spindle, it means if I attach something to motor B, I can get the movement backwards. The wheels will spin in the opposite direction. Makes sense. So now I have attached two motors, and both motors are powered by electricity. So imagine if on these motors I attach them to a battery, and on that battery I put a switch. And that switch, I can turn it on or I can turn it off. So if I turn the switch on, electricity flows and the motor begins to spin. And because the motor is spinning, it gives the car the characteristic movement forward. And if I want to stop it, I just turn it off. And if I turn on motor B switch, I get opposite direction motion, but it's the same concept. People at home, that makes sense? Can I get a thumbs up? So by adding these two motors, I've basically gotten two sets of behaviors. Now I can go further. I can attach a third motor, let's call it motor C, but instead of attaching it to the spindle now, I can attach it to the, let's call it the axle of the vehicle. So if I attach this motor to the axle, I can cause now a movement or a twist in the wheels in the left direction. If I flip that motor and attach another motor, let's call it motor D, and I attach it to this, I can spin or twist this wheel in the opposite direction. So essentially what I have now are four motors, and the motors are labeled. The first motor is motor A, the second is motor B, the third C left, and motor D twist right. So far so good, right? So what we've done, we've created a toy car with four motors, and by controlling the flow of electricity to these four motors, we can get a behavior. In other words, it means for every motor we attach a switch, and that switch is a logic gate. So the nature of a logic gate, it's basically an electrical circuit that can permit the flow of electricity or can block the flow of electricity based on logic. Hence the term logic gate. A gate is a structure that can be open or closed. When it is open, it allows things to flow. When it is closed, it prevents things from flowing. So the gate part of logic gate is basically saying I can permit electricity to flow or I can prevent electricity from flowing. The logic part is the systematic or the reasoning behind what opens the gate or what keeps the gate closed. So a logic gate is an electrical circuit component that can permit or prohibit the flow of electricity based on some reasoning factor. In this case, we can switch on, we can switch off. Does that make sense to everybody at home? So we can switch on, we can switch off. And when we switch on, we switch off, we get behavior. All right. So continuing along with that example, let's say we wanted this toy car to move forward in a straight line. So let's perform an experiment. Let's say we want to pass the car, the toy car, an instruction. So one, let's say we wanted to move forward in a straight direction. What we would need to do is we would need to turn on motor A, which is responsible for the forward movement. But at the same time, we need to turn off motors B, C, and D. That makes sense, right? So by sending these four electrical signals to these different motors, we can create behavior. And in this case, the behavior is move forward in a straight line. If we wanted the car to move back in a straight line, in this case, we would then activate motors B. At the same time, we deactivate or close the gate for motors A, C, and D. A third behavior that we can have is we can have it move forward in a left direction. In that case, we would then activate motors A, and motors C, while at the same time making sure B and D are off. Continuing along, another behavior we can have is forward in a rightward direction. And in this case, we will again turn on motors A and motors D, at the same time turning off B and C. Moving on, if we wanted a fifth behavior, let's say we wanted to move back left, then in this case, we would turn on motors B and motors C, while ensuring motors A and motors D are off. Moving on, if we wanted to give a sixth behavior, we want to move backwards in the right direction, then we would activate motors B and motors D while ensuring A and C are all off. Lastly, if we wanted to have the car just simply stop in position, then what would we do? We would turn off everything, A, B, C, and D. So what we've just done is we've created behavior in this toy car simply by controlling the flow of electricity to each of these components. Remember, we only have 4 motors, but from these 4 motors, we've generated 7 possible behaviors. Straight forward, straight back, back left, back right, forward right, and standstill. Now, what we have here is what we refer to as an instruction set. So what is an instruction set? It's a set of instructions, essentially. So everything here from 1 to 7 is in fact an instruction set. So your computer's processor, your CPU, is basically a set of logic gates that are connected and wired in such a way as to permit the flow of electricity to certain hardware components to control them. So here in this example, we're looking at a toy car. But in reality, this could be a RAM chip. It could be a hard drive. It could be a network interface card. It could be a graphics adapter. It's the same concept, except the functionality is different. Instead of controlling motors, we're controlling other components. But it's still the same concept, on or off, on or off. So as computer scientists and as information technology people, our job is to write instructions that control hardware. So if you're a programmer, that's what you do. You find a problem in real life, you develop a solution, and the solution is going to be a set of processes. You need to now write the instructions to perform an action to solve that particular problem. So how would you write instructions for this toy car, for example? Take a look at this. From the toy car, let's say we wanted to create a scenario where we wanted to write a program for this toy car. So let's say we want the program to drive the toy car from one position to another. So let's say, for example, here's the toy car and it's facing, this is the forward direction. So it starts from this position and we want it to travel this path. So here we have the start and here we have the stop. How would we write this program? It's very simple. Looking at the instruction set, we can use the instruction set, the details in the instruction set, to actually create a small program that will then control our toy car as a piece of, let me just grab this real quick. I want to reduce the size. Okay, and I want to move it across so that we can reference it more easily. So with this instruction set, I can now create some type of behavior. I can map the behavior on the desired outcome. So if the toy car starts from here, this starting position, what instruction do I need to send to the toy car in order for it to get to the stop position? I will first invoke instruction 1. And instruction 1 says, turn on motor A and turn off motors C, B, C, and D. So here, for the movement forward, I will make use of instruction 1. Then when I get to this corner here, in order to turn, I will invoke instruction. What instruction? Instruction 4. Then after it turns, I want it to continue straight. I will again invoke instruction 1 till it gets to this corner and I want it to turn. Then I would invoke instruction 3. Then here I'll invoke 1. Then here I have another turn, and this time it's a left-hand turn. So I will invoke instruction 3 and then 1. And then when I get here, it's a right turn. So I'll invoke instruction 4, then 1. Then when it gets here, I will send instruction 7. So you know when you're writing your Java or your Python, whichever programming language you're learning first, so all those syntaxes that you're writing, it's the human equivalent of the code we've just written. Here, instruction 1, if I was writing it in human language, I will say move forward in a straight line. So I can actually create a programming language where if I say move forward in a straight line, I can configure it to send an electrical signal on a 4-bit channel where channel 1, 2, 3, 4 all represents a connection to each of the 4 motors. Let me draw it if it's not making sense. A computer has a bit count. So in this example, I want you to understand that the motors are A, B, C, D, which means all the communication channel of this toy car that we've built are going to be made up of 4 lines. And on each line, I can carry a 0 or a 1 signal, an on or off signal for the switch to permit or to hinder the flow of electricity. So when I invoke instruction 1, which is turn on A, but turn off B, C, D, the signal I'm actually sending is 1, 0, 0, 0 on the 4 channel. So in computing terms, 1, 0, 0, 0 is my instruction 1. And I can write a program using machine code or using human language. Human language will move forward in a straight line. When you compile that, it will convert 1, 0, 0, 0. And 1, 0, 0, 0 maps to turn on A, turn off B, turn off C, turn off D. People at home, does that make sense? Can I get a thumbs up? All right. So essentially what you've looked at now is basically how computers actually operate. So whatever the program you're writing, at the end of the day, that program needs to be converted into an electrical signal. Think of it this way. As a human being, if you remember from the last week's lesson, you use sound to operate. So as a human being, if you have a document that contains a set of instructions, instruction 1, 2, 3, if you read those instructions and you try to control other human beings, for example, let's say instruction 1 says stand up. In order for you to understand it, you have to read it, or that signal has to come to you in sound. So imagine if I'm your CPU and I want to tell you to stand up. I have to send a signal to you. The way human beings send signal is through sound. So I read the instruction. The instruction is written in text, but I convert it into sound. Say stand up. The same thing is happening here. In a computer program, you have a file, and on that file, you have binary code that is supposed to represent an instruction. So when the CPU reads that code and it wants to recite it to the hardware, it recites it using an electrical signal. And it will transmit that electrical signal over a communication channel, which is a cable. In our example here, our cable is made up of 4 wires. A typical computer is an 8-bit computer, which means all communication line has 8 wires. Modern day computers have 64 bits, 32 and 64 bits, but most commonly 64. So it means all the instructions will be 64-bit channels. So each instruction you can tell your computer to perform, you can have that sequence of 64 bits transmitted as an electrical signal. All it means is the zeros and ones will be transmitted to the appropriate device depending on the function you want to execute, and then it can perform an action. Here at the same time, if we wanted to add a new piece of technology, let's say we wanted to add air conditioning to the toy car, we can add an air conditioner controller if it's just on off. If we wanted to be able to control the thermostat of the air conditioner, we can add another switch that can change the value of temperature up or down. The more complicated we have, the more channels in our instruction set that we can actually set. Or we can create separate channels, one for controlling the car and one for controlling the onboard technology of the car. So we can have 4-bit here and 4-bit to continue to perform another action. So that's the basic gist of it. This is how the technology actually works. So the switches that control the on-off feature are the logic gates. And when you give a computer an instruction, the way it interprets the instruction is by also use of these logic gates. So in other words, if you tell a computer to do something, what you're really telling it to do is turn on certain things and turn off certain things. Just like we saw in this example, telling the computer you want to go straight forward in a straight line is you basically turning on motor A and turning off motors B, C, and D. So if I, for example, let's say I select this image and I right-clicked on it and I said I wanted to copy, that copy command is again sending a signal to the computer using zeros and ones. The computer interprets it and performs the action by controlling certain hardware components, turning certain things on, turning certain things off, and you get this behavior out. So far, so good, everybody? So far, so good? Now we can begin the lesson proper. So that is the, if you like, the introduction. So let's just jump into the slides and take a look at a few concepts before carrying on with the main gist of it. I'm going to try and keep it interesting so that you don't get mentally fatigued. So here now, we need to understand that these logic gates, although we said they are circuits that control the flow of electricity, we have different types of gates, and the way they operate, they all do the same thing: permit or block electricity. But the way they function to permit or block electricity is based on certain reasonings, which are what the logic part of the logic gate is. So we'll look at the different types of gates and how they behave. Now, in this logic gate system, there's a special kind of mathematics that we have called Boolean algebra. The Boolean algebra mathematics allows us to be able to evaluate the behavior of a circuit. Just like when I demonstrated this toy car example, we saw in the toy car how it can translate, how these signals can translate to behavior. So in Boolean algebra, we can also see how a set of signals can be translated into an operation or a function. And we'll take a look at that. So you will actually see how a computer can do addition, subtraction, multiplication by simply controlling the flow of electricity. It's quite interesting. There's also something called a truth table, which we will demonstrate, which is a table that allows us to see all the possible inputs and outputs of a circuit. And then we also want to learn how to design diagrams. So let's carry on. At the end of the day, we want to be able to define logic gates. What is a logic gate? A logic gate is a circuit component that can control the flow of electricity based on certain conditions. We want to be able to discuss the characteristics of these logic gates. So we have to see the types and how they behave first. And that's what we're going to begin. But before we begin that, let's take a look at what actually makes up a logic gate. The first thing you want to understand is, what is a circuit? A circuit in engineering is basically a closed loop. And that closed loop allows the flow of electricity. So if a circuit is open, we say it can't allow electricity to flow. So on off means closed circuit or open circuit. If it's open circuit, that means electricity can flow. If it's closed, it means electricity can flow. So the integrated circuits are what computers are made up of. In other words, one circuit combined with another circuit combined with another circuit makes up a digital device. Just like for human beings, group of cells forms tissues, group of tissues, organ, group of organs, system, group of systems, organism. So same thing. So each function you have in a computer is a circuit. So take, for example, I have a CPU. It's a circuit. It's an integrated circuit because there's more than one circuit in it. Your RAM chip also is circuit. It's an integrated circuit because there's more than one circuit in it. Your network card, your graphics adapter, your sound card, all of these, your screen, all of these are separate circuit elements that are integrated. So you can have a circuit integrated with other circuits, integrated with other circuits to form a complete device. So this is why we say computers are built up of integrated circuits, ICs. These ICs are, you can find them in the CPU. The bus is a cable, the interface, memory, and so on and so forth. And they're made up of three fundamental components. Just like I can say a cell contains a nucleus, a cell membrane, mitochondria, and so on, I can also say this integrated circuits are made up of transistors, resistors, and capacitors. So this is what a transistor looks like. You can see it's a device that is made up of silicon that has 3 pins. And if you remember, I said a logic gate controls the flow of electricity. So in this sense, what you're actually seeing is this. What you're actually seeing, let me see if I can draw on this. What you're seeing here is this. This first pin is the in pin. This is the out pin. So electricity comes in through this first pin and leaves through this first pin on the condition that the gate is closed or open. So this third pin in the middle, if I send it a 0 signal, I'm telling it to close the gate. So whatever electric signal is connected to the in pin will not flow out. And if I turn it on, it will send a signal to open the gate so that the electric current can flow, whatever the signal in here is. So basically, this is the switch. So I can attach this transistor to my motor. So the power cable goes into the in, the out goes to the actual motor. And then I have another pin in the middle that I can send the control signal, which is a 0 or a 1 to open or to close the gate. Then I have next here a resistor and a capacitor. What is a resistor? A resistor in electronics is just a small device that reduces the amount of current that is being transmitted. Think of it like me reducing my volume. If I'm speaking at full volume, my voice is very loud. And if I reduce my volume reduces a little bit. So that's what a resistor does to an electric current. If the current is high, the resistor reduces the power or the energy in the signal. Why does a resistor need to exist? Because some of the components inside your computer are very delicate. Your wall socket provides 240 volts. That's too much for any delicate equipment inside your computer. So your adapter reduces that 240 volts usually to between 9 to 19 volts. But internally, some devices can only deal with 5 volts or less. So for every device that needs less current, you attach a resistor to it. So the resistor is just to control the amount of electricity. It's not our business. Our main interest is the transistor, which is the main part of the gate that opens or closes. But we need to know that resistors exist. And then you have these things called capacitors. The best way to imagine a capacitor is like a battery. So if you have a big battery and you have a small device, maybe the big battery can power the device for 6 hours. If it's a smaller battery, maybe 1 hour. So the capacitor is a very tiny battery that holds a very small amount of current for sensitive devices. Now, the reason why the capacitors exist is to ensure the smooth transition of current or signals from one device to another. What do I mean? Think of it this way. Right now, as I'm speaking to you, my lips are forming sounds that make up the words that I'm saying. So for example, if I wanted to say cat, it's a combination of the C, the A, and the T sound. So if I put it together, cat, it transmits through the air and it reaches you. I want you to imagine a scenario where maybe this place is so noisy, and when I'm speaking to you, maybe the signal is not constant, it's fluctuating. So some parts of it are loud, some parts of it are loud, and some parts of it are not so loud, and some parts of it are missing. So it will cause like a fluctuation, a gap. In other words, let me draw this out so that it makes a little more sense. So let's say, I'll give you a very simple example. Let's say I have a tank that contains water. And inside that tank, I have like a pipe that opens up the tank and the water can flow. As the water is flowing, if the water is heading to a particular destination, what can happen is any interference on the lane of the water can reduce the pressure or the flow of the actual water. In case, if there's any obstacle on the road, the amount I'm allowing out may not be equivalent to the amount flowing in constantly. So let's say I'm sending the water at 5 liters per second. If there are any interruptions at the destination, I won't be getting 5 liters per second. I may be getting 3 point something liters per second. And sometimes I will get 5, but it will fluctuate. So in electricity, if I have a battery and the battery is providing a current, that current might not be constant. So it will go up and it will go down. It will fluctuate. And if it's going up and down fluctuating, it will destabilize the electronics in the system. So what we implement to prevent that is a capacitor. So the capacitor is like a bucket that stores electrical energy. So the battery, like the tank, will pour electric current into the capacitor. And the capacitor is directly connected to the actual device. So by topping it up, even if there's an interruption in the flow of electricity, this guy always gets his current at the stable range. Now, if the last 5 minutes didn't make sense to you, don't worry. We went overboard with the explanation from an engineering point of view. All you need to know is this, that one, we are particularly concerned with the transistors, which are what controls the circuits, whether open or closed. The capacitor is just a battery. The resistor limits the flow of electricity. It's like a tap. The more you open it, the more current passes. You close it a little bit, it reduces the current of water. It's just a tap. So if you take a look at a naked computer, this is what you see. If we zoom in to this, you can see all the black chips here are essentially logic circuits that are made up of logic gates. Now, if we wanted to take a microscopic view, if we wanted to really go in to see the view of this, there's a document that I have attached inside your work called one of the logic gates documents, which is here. And I can take a look at this particular document that shows us what these chips look like on the inside. So I've attached this for you to read on your own later on. So I'll just zoom to the page that I actually want. So here you can see an example of a chip. So this chip is actually made up of logic gates. And you can see here each chip has pins. These pins can represent wires for input or wires for output. So this particular chip that we're seeing is the 7400. And the 7400, this is its architectural diagram. These symbols here are logic gates. So you can see pin 1 and pin 2 are input pins, and pin 3 is an output pin. We'll explain what this means all later. And then for the battery or for the electrical supply, you can see the negative is pin 7 and the positive is pin 14. So in other words, if I wanted to power on this chip, I would attach the positive terminal to pin 14 and the negative terminal to pin 3. So the chip now has energy, it has power, and it will control the flow of electricity based on the signals I put on the input pin. It will generate an output. So this input pin that you're seeing, how many pins do you see? There are 2 pins on the in and 1 pin on the out. So inside this is a set of transistors that are controlling what electricity will flow out of these input pins. Does that make sense to everybody? So let's take a look at the logic circuits in specific. So now the lesson really begins. So we jump back to our whiteboard and we'll begin looking at the first of the logic gates. So the first of the logic gates we will begin looking at is the NOT gate. The NOT gate allows us to implement the NOT logic. First, we will look at the symbol. The symbol is a triangle with a bubble on it. This particular gate has the characteristics that it can only allow one input, let's call it A. And when you put in that input A, what you get transmitted out is the opposite of A, which is represented by A bar. Another way we can represent the opposite of A is by using A with the apostrophe symbol. So these two things mean the same thing. So here we have the symbol, and here we have the equation, the Boolean equation, the mathematical representation of the logic gate. So if I wanted to write a NOT gate, I would basically write whatever the input. It could be A, B, C. A just means variable and unknown. It could be A, B, C, but if I put the bar at the top or the ampersand or the apostrophe to the side, it means that this is the opposite of A. So if A is 0, it means the output, if it goes through this logic gate, is 1. It's the opposite. And that is what the truth table helps me evaluate. So the truth table will allow me to look at all the possible inputs of this circuit. Since it only has one input, that input is labeled A. A can be a 0 or a 1. So the table shows me all the possible inputs, a 0 or a 1. And the output, let's call the output X, the output for a NOT gate, if I have an input A, is going to be two possibilities. If the input is 0, the output is going to be a 1. And if the input is 1, the output is going to be a 0. So what are we talking about here? I need you to understand something. These signals that are electrical, that we say 0 and 1, I don't want you to think of 0 as electricity absent and 1 as electricity present. No. 0 is a signal. Just like in English language, I don't keep quiet to say nothing. I say nothing. Nothing is a sound, and something is also a sound. But it's used to represent two different things. So I can say something or nothing. I'm still producing sound. So the 0 is also an electrical signal. So when you look at the logic gate and you see, we say if it's a NOT gate, 1 goes in and 0 comes out, remember 0 is still a signal. We're just converting the 1 signal to a 0 signal, or the 0 signal into a 1 signal. So it's still signal. It's not on, off, technically. It's just a signal that represents I should be on or I should be off. So it's kind of like I can turn you on or I can turn you off. If you get what I mean. Right? So I'm still doing something. Right? It's a weird example, but it's the only thing that comes to mind. So 3 things I'm looking at here. I've looked at the symbol, I've looked at the equation, and now the truth table. It's important for you to understand what these things mean. The symbol are just characters, just like I can learn English language, I can learn the symbols that represent the logic of the logic gates. The equation is the mathematical representation of the symbol. And using the equation, I can represent reasoning. That's a very strange statement if you think about it for a second. How do you represent reason? For example, let's say I have 2 objects in front of me. So let's say I have these 2 objects. Looking at the screen, these 2 objects. Let's call the first object on the left-hand side object A, and the next one object B. Which of these is bigger, A or B? Obviously A. If I tell you represent your reasoning, describe how you evaluated which is bigger, prove it. And I want it maybe in written form. What calculation did your brain perform to give you the answer that the first object, object A, is bigger than the second object? It's very perplexing. What is the reasoning in your own head as a human being that taught you and confirmed to you that A is bigger than B? Huh? But what is the reasoning you're applying? The point is, you can perform the action instinctively without thinking too hard. You see something, oh, this is obviously bigger than that. But now imagine if you are going to represent it as a set of instructions that you have to write for a computer program to be able to repeat the action you performed. How difficult do you think that's going to be? You can do it, but can you write a program that tells a computer with 0 intelligence how to do it? It's very difficult. And this is what we call reasoning. This is why